controlled half wave controlled rectifier circuit with resistive load. Instead of using this diode, if I replace this diode with a SCR, SCR is what? SCR is just same like the diode, but I have one more terminal. Okay, this is anode and this is cathode. Okay, and this is a gate. So if I apply the gate signal, then I can operate this SCR. This is SCR. SCR operation is same like the diode. So in the diode, if you apply positive and negative, then it will be forward biased. It will start to conduct. But in SCR, even though you apply positive, negative, if you do not apply the gate voltage, then there will be no conduction. So it will wait for the gate signal. So once you give the gate signal, then only it will push the conduction between anode and cathode. This is the circuit. I am applying the input. I am using SCR instead of diode, and the output I connected the resistor. This is the output waveform. Actually, for this circuit also, we have to find all these parameters: average value of the output voltage, output current, RMS value of the output voltage, output current, load power, and so on. Here, what is happening? Here you can see here what is happening. This is the input signal I am applying at the input. At the output, okay, I am also having the firing angle, the IG, gate current. I am applying the gate current here. I want to tell one more thing before I continue this one. SCR can be operated in 3 different modes. Okay, so let us draw the SCR now. SCR like this. This is the gate, and this is the anode, and this is the cathode. So when I apply the forward bias, if I don't apply the gate voltage, then this SCR will not conduct. That is called forward blocking mode. This is a forward blocking mode. You apply positive, negative. It means this SCR is already forward biased, but still no conduction. It's blocking the current flow from anode to cathode. That is why we call this as a forward blocking mode. And another one is called forward conduction mode. Forward conduction mode means you are already applying the gate voltage. So you are applying the gate voltage. Then it becomes forward conduction mode because it's already in the forward bias and you are applying the gate voltage, then it starts the conduction. Forward conduction mode. And the third one is called, let me take another pen. So instead of giving the plus and minus here, I reverse the polarity, minus and plus here, minus to anode and plus to cathode. So we know according to the basic diode, whenever you change the polarity, the power supply, and then it will be in the reverse biased. So this mode is, then it will not conduct anything. Even though you apply the gate voltage, if the polarity is changed, minus and plus, then this SCR will not conduct, it will block. So it will be in the reverse bias. So this one is called reverse blocking mode. So now you should know that forward blocking mode, we don't have a gate signal, even though it's forward biased. Forward conduction mode, the SCR is conducting because it's in forward bias and also there is a gate signal. And third one is called reverse blocking mode. It's in reverse bias. So there is no current. It's blocking the current flow. Okay, these three are based on the 3 modes we are using. We are operating the rectifier. So here you can see the operation. Where is the waveform? So this is the waveform. Let me take my cursor. So this is the waveform, output waveform. So here is the input voltage and here is the output voltage. and this is the firing angle. And we are talking about half wave rectifier. It can conduct only half wave of the input signal. So the positive cycle only will be conducted by this SCR because we have only one SCR. So the positive cycle has 0 to 180 degree, right? So I am applying this positive cycle to this SCR. So, but I am not giving the firing angle immediately at 0. I am giving the firing angle, the gate voltage to this SCR after some time, maybe after 5 seconds, or maybe let us say we are talking about omega t, right? With respect to phase and the frequency. So I can say I am giving the gate voltage only at 30 degree. So 30 degree, let me take my pen again. Maybe I am giving the alpha 30 degree. At 30 degree, I start to give the input to the gate. So instead of starting the from 0, I am starting the conduction only after few seconds at 30 degree. So it means what? It means the output, you will get the output only between 30 degree to 180 degree. You know, pi is equal to 180 degree. So you will get the output voltage only between 30 and 180 instead of 0 and 180. So instead of giving the alpha is equal to 30 degree, now I fire at 60 degree. It means at 60 degree, I am giving the gate signal. So at 60 degree, maybe it's somewhere here. Then the firing angle will, so you are already, the SCR is in the forward bias because it's already positive, negative, right? The first half of the cycle is positive, negative like this. The forward, it's in forward bias mode. But according to this forward blocking mode, because there is no gate signal, even though it's in forward bias, this is not conducting. There is no current conduction. So after I apply the gate signal only at 60 degree now, then it start to conduct, and then it will change to the forward conduction mode. Okay, forward blocking to forward conduction mode. Then, for example, at 60 degree, I give the gate voltage and then it start to conduct. So maybe the output starts from here and then the pulse width got changed. Instead of like this 30 degree, now I am 60 degree. So this is called firing angle. So when I increase the firing angle more and more, you can see the pulse width got reduced more and more at the output. So if you make the average of these small pulses, you will get small DC voltage at the output. Maybe you will get plus 5 volt. But if I increase the width more and more, then you will get, when you make the average, you will get more DC at the output. So you can increase or decrease the output pulse width by changing the firing angle. So if you increase the firing angle, the pulse width will get reduced. Remember, so 30 degree, I have the pulse width like this, all the way from here to here. At 60 degree, the pulse width became shorter. So I increased the firing angle from 30 to 60. So the output got reduced. That is the concept. So you should understand, by increasing the firing angle, what will happen at the output, that you can check in your lab experiment. Okay, so this is the operation of this rectifier with SCR. This is called a controlled rectifier. Okay, so now we have to derive the formula for this controlled. Remember, this is a controlled rectifier because I'm using SCR. Average value of the output voltage, VO average, is equal to 1 divided by 2 pi. We know the periodic angle of every single full cycle is 2 pi, 0 to 2 pi. So 1 divided by 2 pi. Here the conduction is only between alpha to pi. So the limit is alpha to pi, and then the output is equal to the input. So Vm sin omega t d omega t. So I am taking this Vm outside. So Vm is, because it's a constant amplitude value, Vm divided by 2 pi. This sine omega t, if you integrate, it becomes minus cos omega t d omega t. The limits are alpha to pi. Why I am not taking the limits 0 to alpha and then pi to 2 pi? It's very obvious, right? Here you can see alpha to pi only I am getting the output. 0 to alpha, there is no output. Output is 0. And then from pi to 2 pi, output is 0. So I am getting output only between this area. So I am taking only this area, alpha to pi, alpha to pi, alpha to pi only we get the output. Okay, so now integration becomes minus cos omega t and you apply the limit. So it will become like this. If you apply the pi instead of omega t, then cos pi is equal to -1. That is the formula. And then you are applying the alpha here, then it becomes minus into minus, it becomes cos alpha. So you know, when you apply the limits, you have to apply the upper limit minus lower limit. So this is already minus, and here we have another minus, so it becomes plus cos alpha. So minus into minus, minus times minus, is there is a plus. So 1 plus, this becomes 1, and cos alpha is as a cos alpha. So Vm divided by 2 pi, 1 plus cos alpha. This is the formula for VO average, the average value of the output, average value of the output. So if you increase the alpha, then this VO average will decrease. By varying the alpha, by varying this alpha, we can change the output voltage. This is called controlled rectifier. That is why we call this as a control. We are controlling the output voltage by changing this alpha value. Okay, so this is called variable output. Simply we call this as a controlled rectifier. Okay, so if alpha is equal to 0, let us say alpha is equal to 0 degree instead of 30 degree, 60 degree and so on. If I make the alpha as 0 degree, what will happen? This is a controlled rectifier. I am making alpha as a 0 degree. It means there is no firing angle. Firing angle is starting immediately at 0 level. So it means the output will be the full output for one cycle. Then this is same as the uncontrolled rectifier, right? In uncontrolled rectifier, what we are getting? We are getting the output from 0 degree to 180 degree. This is a uncontrolled rectifier because it's a diode. So in the controlled rectifier, SCR, we are making the alpha as a 0. Then we get the output from 0 to pi, same as the diode. So you should remember this. Whenever alpha is equal to 0 in this SCR, so it means like you are applying the gate signal immediately at 0, then the output is equal to the uncontrolled rectifier. So that is what I mentioned here. Alpha is equal to 0, then the output is same as the uncontrolled rectifier. So now we found the VO average. What is the IO average? The formula is VO average divided by R. We know already VO average. So just to put this R in this formula, Vm divided by 2 pi R times 1 plus cos alpha. This is the formula for IO average and RMS voltage. So VO RMS is equal to 1 divided by 2 pi, the periodic angle. You should not forget this. In all the formulas, in everywhere you use, this is one cycle. One cycle means it starts from 0, ending up with 2 pi, 360 degree. And the limit is alpha to pi because we are in the controlled rectifier. It can conduct only from alpha to pi at the output, alpha to pi. So alpha to pi, and this is RMS square value. I already said how we can do that RMS. So that is a square root of means average, square root of RMS, right? RMS means root. Root means square root. I put 1 by 2 here. Mean means average. I find the average by using integration formula mathematically because this is a continuous infinite samples, and then I use the square. So the input power is equal to output power. So Vm square sine square omega t d omega t. The limit is alpha to pi and the periodic angle, and then the everything whole power square root. The power of 1 by 2, it means it's the square root. Okay, so if I put square root, then I have to take out this 1 by 2. Okay, so Vm, I'm taking it outside of the square root, so it becomes Vm divided by square root of 2 pi. This is a constant now, separated from the square root. And then we are still using this alpha to pi. So sine square omega t, the formula is 1 minus cos 2 omega t divided by 2 d omega t, the whole power 1 by 2. And what is happening now, I'm taking these two outside. So just this is rearranging these two. When it comes outside, it's going to be a square root. So square root of 2, square root of 2, square root of 2, and then it becomes 2. So that is why here it becomes 2 times square root of pi, and then 1. Now I'm applying the integration formula. 1 becomes omega t, cos becomes sine 2 omega t divided by 2, because this is cos 2 omega t. So the constant should be, this is the standard formula. The limit is alpha to pi, and then entire the whole power 1 by 2. This is a constant. So V RMS is equal to, now I apply the limit, so it becomes pi minus alpha plus sine of 2 alpha divided by 2 whole power 1 by 2. This is the formula for VORMS of controlled rectifier, and IORMS is equal to VORMS divided by R. You can apply this R into this formula, then you will get, of course, this VORMS, or you can say in the other way, you apply the VORMS equation here, then you will get IORMS. And PO average is equal to VORMS times IORMS, P equal to VI. That is the standard formula for power calculation. So you already know what is VORMS, what is IORMS. You apply here, you will get the PO average. And the PIV rating of the diode, or sorry, here SCR. So SCR PIV rating is equal to the maximum value of the output power, that is the VM, the magnitude of the applied signal. And conduction time is T is equal to pi minus alpha divided by omega. So because the conduction time, SCR is conducting only between alpha to pi with respect to omega. And circuit turn off time. So how, when the circuit will be turned off, because in the SCR, the circuit turn off is also important. We can simply call this as a TC is equal to pi divided by omega. This is also the standard formula. You should remember, if you want to turn off the SCR, you really have to change the polarity, and then you have to maintain this reverse polarity from pi to 2 pi. From pi to 2 pi, this is a negative pulse, right? So SCR is in the reverse bias, then it will not conduct anything. So there is circuit turn off time, and the input power factor, the same as what we had seen in the previous one. Cos pi is equal to P average divided by VSIS. P average is, that is the VORMS, IORMS, and then the VSIS is here. IORMS is equal to IS, so we can cancel this and this. So the input power factor is equal to VORMS divided by VS. So this is the formula for this one. So far we had derived all the formulas for this controlled rectifier. So we know VORMS, IORMS just here, and then the other factors. And we have already derived average output voltage and average output current, this formula. So please try to remember these formulas, or at least you should be able to derive this formula by yourself. It's kind of straightforward. If you know some integration formula, and if you know the flow, the steps, then you can easily calculate this. But all the rectifiers are using the same principle. They are using either diode or rectifier, SCR. So if you use the diode, you cannot control anything. The conduction starts from 0 to 180. If it's a half wave, If it's a full wave rectifier, the conduction is from 0 to 360 degree. And SCR means you can change the angle, the firing angle, wherever you trigger the SCR at particular angle. At that time only you are giving the gate voltage, and then the conduction starts. And this is a small problem. I also had given the sample solution in the PowerPoint. You can take a look at it.